another episode of Microchip's live stream. On this week, we're going to talk about exploring the code behind the IoT development board. And my name is Matt Dickens. For those of you that are watching for the first time, I'm normally in the back of the booth, but today I got the honor of privilege of being out here with a couple of my friends, talking a little bit about the software. So I'm here with Chris Tucker, who is an applications engineer, as well as Madhura Mujumbar, who's also one of our applications engineers in 8-bit. Some of the great minds behind that software that we're going to be talking about today. But before we get started, let's jump to the back of the booth, and Wayne and Ricky can tell us a little bit about kind of how you guys can be involved in part of the live stream today.
Hey, how's it going, everybody? As Matt said, my name's Ricky Johnson, and to the right of me, I've got Wayne Freeman. How's it going, Wayne?
It's going really well. How are you?
Pretty good. I'm pretty good. Excited to be here, so ready for a good live stream.
Good. I was a little worried about you a little earlier.
Don't worry about it. The coffee's kicking in,
cool.
So we're good to go.
Nice.
So there are a few ways that you can stay active during this live stream. So we have a chat window that we hope that you comment any questions that you might have, or if you just want to say hey, throw that in there. Additionally, you can email us at livestream@microchip.com. We also have some giveaways going on today. And Wayne, do you want to talk about this, or you want me to take care of it?
Let's see. Well, I guess we'll tag team it. So
okay.
Basically, we're actually giving away one of two IoT development boards. So basically, I think what we'll do is we'll give you we'll do 5 giveaways, and we'll give someone the choice of whether they want a PIC-IoT or an AVR-IoT board. So what you got there in your hand is the AVR-IoT board. You want to spend some time discussing the ins and outs?
Yeah. So this is the AVR-IoT WG evaluation board. So it's great for rapid prototyping. It has a Wink 1510 Wi-Fi module on it, an ATE CC608 secure element on it, and an ATmega 4808 microcontroller on there. So it's smart, secure, connected. You're able to get connected to the internet in 30 seconds or less. So, Like I said, great for rapid prototyping and cool to play around with.
Yep, and I don't have much to add about the PIC board other than the fact that the microcontroller is different. It's got a PIC-24 microcontroller on it. And it's funny that we chose these boards for the giveaway this time, because that's what we're going to be talking about today.
Yeah, you're right. So I think that's all that we have back in the booth, so hopefully you'll be seeing us again soon. But for now, we'll send it back over to the front desk.
Yeah, thanks, Ricky. So that's exactly what we're going to be talking about today, and specifically talking about the firmware that's making that whole system kind of run together. So on that note, we'll jump in and get started. So Chris, before we get started and talking about the nitty-gritty of what's actually going on in the software, what kind of new features or things can people be looking for as they dive into the software and are exploring it for the first time?
So we have a couple new software libraries that came out basically to support the AVR and the PIC-IoT board. Inherently, what we've done is we've improved the underlying drivers that exist inside of the Foundation Services library set. So we'll discuss those coming in a little bit, but that gets into where our scheduler is going to come into place. It has to do with reading from our ADCs, handling all of our sensor measurements, doing our communication buses such as I2C, SPI, UART, and all these things. And by being underneath Foundation Services, that basically becomes your foundation layer for your entire architecture of your system to build up from. So those lower levels have been continued to be improved. We've integrated new things into them, such as the scheduler that we'll discuss in this video. And then further, we've created the Wink 1510's isolated software library. We created an MQTT stack that is used to support this demonstration. That's going to be going through quality of service level 1, supporting level 0 as well. In the future, we'll be supporting future ones. And then we've also integrated the crypto authentication library that is going to be used as the software driver library that supports the AECC 604 encryption device.
Sweet, awesome. So a lot of great software underbelly tools that people can use and modify and kind of build this board off of. Great, so you talked a little bit about the scheduler, so that's probably a good place to start. Can you tell me a little bit about what the purpose of the scheduler is and what it's doing, and specifically what it's doing within kind of the AVR software and PIC software?
Sure. So over the past few years at Masters event that we do for some of our colleagues throughout the industry, we've taught classes over firmware design, and then one of the ones that I specifically taught was our task scheduling, no RTOS task scheduling, no RTOS required.
Yeah.
Basically what that gets into is preemptive and cooperative execution of code, and then some of the nitties and the gritties of basically working with a complex application and the ways that you can do different patterns of implementations to improve the robustness of the design.
Cool.
So that goes into a lot of high-level detail or low-level detail regarding that subject. So actually the scheduler, the timeout driver that it's called inside of this implementation, is going to actually be like an RTOS Lite.
Okay.
It basically works off of a very simple linked list system. You tell it what callback or what function you want to be called at a periodic rate, and you basically schedule it at what rate you want it to be called back at.
Okay.
And then if you want it to become a repeated task, at the end of that function, you basically will reload the scheduler. Otherwise, if you just want it to elapse and time out, then you just load it with a 0, and that task won't be called back until you create the next scheduled task.
Okay, cool. So it's kind of allowing certain functions or different things to be repeated on a particular schedule, hence why it's called the scheduler. Awesome. And if you want to check out Chris's video, we actually have that included in the description. And if it's not there now, we'll make sure that we have it included after the fact. So I know that that's a great video. It's been super informative to a lot of people. One of our more popular videos, especially regarding firmware. So that's a great video to check out if you have no idea what we're talking about when you hear the term scheduler, stuff like that. Definitely check that out after the live stream. Well, great. So with that being said, and just kind of keep that word scheduler, task scheduler, and callback, we're going to continue talking about those terms in the live stream. So keep those things fresh in your mind. But with that, let's go ahead and jump into kind of the firmware and what we're talking about today.
Right.
If we want to switch over to my screen, we can kind of show people where we get started.
So I did want to talk about the scheduler because in the end, that is the crux of the entire application. We'll see how it makes the application extremely simple in the end once it's actually executing.
Cool.
So initially what we have is the first part of our startup system. So this is the smart aspect of working with a microcontroller. So this is where we initialize our hardware so we configure our I/O pins, where our push buttons are going to be, what LEDs are connected to what, which peripheral pins physically are connected to the module devices, so which one of the pins on the microcontroller relates to the SPI communication and how it connects to the Wink driver, which ones are the I2C connections that connect to the encryption device, I2C that's also used to take measurement from the temperature sensor. So that's a shared bus, and Foundation Services inside of the I2C instance works under an open-close principle. And so what that allows you to do is you open the instance saying I am talking to this sensor or I'm talking to my temperature sensor, whichever one it may be.
Gotcha.
And then for that, as it opens, it initializes the bus according to the way that it needs to operate. It does the data communication, and then it closes it, basically de-initializing it. So the next time that it needs to communicate on that bus to a different device or possibly even the same one, you reopen it on that instance of who you're talking to.
Gotcha. Cool.
So that...
Just to pause you real quick. It looks like we got a question from the booth. If you guys want to shoot over there, and what's that question?
Hey, so we do have a question from Juan, and Wayne, you might have to help me out with some clarification. I'm not the brightest guy ever, but I think what he was, I think what he was asking is the scheduler compared with the RTOS? Do you think that's what he is?
Yeah. It looks like he's asking if how the scheduler that we're using for the IoT boards compares with an RTOS. And if it is, there's a couple of follow-ups. It looks like he's asking if it's using something that is a known RTOS or if it's something homegrown.
No, so the scheduler itself is actually based off of the timer peripheral that's ingrained inside of the microcontroller. So in this case, it's just based off the 16-bit peripheral timer, timer 1. We derived it actually from the Atmel Studio collection of software libraries, and we've integrated it inside of the MCC solutions as well as bridging over inside of the Studio-based solutions. It is basically just working off of a very simple linked list system. So as you schedule tasks, if the next task will take a longer rate, then the system itself is smart enough to know the delta of the time and will insert it into the queue of the list. So basically it's executed as that task needs to occur. So if you have half a second and then a 1 second, it'll figure out the times and figures out where it needs to be slotted inside of the list. And you as a user just had to create the request to execute it at a periodic rate. So that's basically how it works. It's really low-level implementation of what an RTOS does. RTOSs will be able to branch you off into larger implementations, such as round robins, priority scheduling, mutexes, and the way that you'll handle different threads. But we're an 8-bit system, and so on an 8-bit system, that's way more overhead than we need to typically carry. And so with what we needed inside of this implementation was a callback every 50 milliseconds, which is a requirement according to the Wink software driver system. And so the timeout driver was perfect for us. So we just created a callback that I'll discuss here in a little bit that's called every 50 milliseconds to basically ask the Wink driver if it needs to handle a request inside of its inner driver system.
Awesome, thank you. And thank you, Juan, for the question.
Yeah.
One of the things that I do want to mention, because Ricky and I have a list of things that we needed to mention, and neither of us looked at the list earlier. Make sure, if you're not subscribed already to our channel, subscribe, smash the like button, hit the bell.
All right. Thanks, Wayne.
All right.
Awesome. So like you said, we're going to talk about callbacks, I think, coming up right here. But Wayne, if you want to switch back to my computer real quick, we can just point people out. So we just talked about the initialization, and now we're jumping on to the LED test.
Yeah, so basically, just like you always do through MCC, you initialize your buses, your I/O pins, however you're going to communicate. That's your hardware level, your HAL.
Yeah.
So that's right there at your MCC start point. Then we do an LED test, so we basically just blink the LEDs on the board to confirm that all the functionality is there and to indicate that we're in our startup process.
Cool.
So after that, we're going to get into our command line interface. The command line interface uses the simple UART over the foundation services, and it is our first timeout that's basically scheduled.
Okay.
And that one basically says every 50 milliseconds, I want you to call back into my CLI task handler, where it will, if a byte is available, parse that byte and then go through the message responded over the UART terminal to do an action.
Gotcha.
So that's all you need to know about the CLI. It basically is created as a task here.
Okay.
That's
cool.
it. So if we just continue back down, so then at this point we just have a debug instant, the debug. So it just starts the debug printing, which is basically over the UART.
Cool.
And then we communicate with our crypto authentication library. So this is where we're going to use our I2C driver, also carrying over inside of the foundation services as a whole basic layer. So if we go to the next slide, this is just real quick a review of basically the way that scheduler will work, how you create the scheduled task. It works off of just a simple timer, which is any one of the peripherals. So we use the timer 1, so it's a 16-bit timer peripheral, but you could use timer 0, 2, 4, whichever implementation you want. It just depends on the level of resolution or how large of the tick values you want to deviate.
Yeah.
Once again, this is just inherently part of foundation services, so it's already out there as a software library. You can add timeout driver completely independent. It will work for any application you want to develop.
Yeah.
It's just ideal for the Internet of Things applications where timing is very specific and very important.
Cool.
So once again, at the very top there is where you would actually have inside of a function. That's where we're basically creating the timeout. I point to where the function that I want to get called at. And then that define that you see on the right, the CLI task interval, is just the rate that I wanted to do. So this is just a define somewhere in there that's at 500 milliseconds.
Yeah.
So inside your prototype or inside your source files, you'll basically have a reference to that CLI task timer. So once again, you see that as the task that was created. And then the reference to the CLI task is the function that you would actually see in the code. So that means I can go directly into the CLI task function, and I know that that task and only what's happening in that function is what gets occurred and executed every 50 milliseconds.
Awesome.
So you want to make the throughputs of all of those relatively short, but you can make the, you basically are encapsulating all the application's functionality in one location. So it's very easy to debug because you say, well, at this part of my application, I'm only inside of this one API.
Sure, sure. So if I see a particular issue with my program or there's something that I'm like debugging really hard, I know immediately where to go to try to debug that.
Correct.
That's
and
awesome.
It lets us isolate it into more specific features of the application, which we'll get into later, which is basically, am I in my main while loop application or doing some kind of cloud or TCP based
Sure. Awesome.
So once again, that is the example of the function. So CLI task was where I pointed to. That's the function. You basically will get into it. You'll do some work inside of there. And then at the bottom of it, one more click. you'll see where the return is, and that is where I'm reloading it. So basically, I've scheduled a task initially when I created it, and by returning that value again, I'm rescheduling it. I'm saying refire. So if I had just returned a 0 there, then I'm basically saying you fired once, whatever you've completed at this periodic rate or at this scheduled rate, you are now complete from moving on. So then I can recreate that task later, and it'll execute then once more.
Okay, awesome. Cool.
So then here we get into the secure part of the application. And once again, this is all within our application manager. This is just where we initialize our system, and then we'll use the scheduler to actually do our application behavior.
Gotcha.
So this is where we're getting into the secure part. This is going to use the crypto authentication library software library that you can generate out of MCC, and that supports many of the ECC products out there.
Great.
This is going to be where we get our unique user ID, the UUID. And so basically by asking the encryption device, what is your unique device ID, we're able to append that onto our device so that when we get onto the internet, we are unique to the entire web, and that's what you'll actually see appended to the back of the URL when you load the ClickMe file.
Cool.
And that basically is what gives us our name. So all of this is done over simple I2C communication to that IC device. It gets the information, it confirms it's able to do communication back and forth, and then it grabs the UUID information. And that is basically all we needed to do for secure. We know we're talking to the encryption device, we can exchange information with it, and we got some unique information from it that we can append to our application. So that when it goes to the web, it's secure.
It's secure. Awesome. Yeah, Wayne, we got a question in the booth?
Yes, we do actually. We have a few questions.
Yeah, a plethora of questions, if you will.
It seems as though the people here are here to learn.
They're curious.
Great.
Good. I love teaching.
Right.
So we're going to throw a bunch of them at you. Go ahead.
So the first question comes from Jared, and it's about power consumption. So he wants to know how he can reduce the amount of power consumption that he has on the AVR-IoT board. He's hoping to get about a week of battery life out of his current application. Do you have any tips for him?
So we don't do any sleep inside of the main application. What you can do is inside the, this gets pretty complex, so I'd probably say email us afterwards. By the end of the entire live stream, you should have a better architectural understanding of where to get into the API calls. You're probably going to want to be inside the main task callback. And then you'll probably want to implement some of the sleep features that are available on the plethora of PIC and AVR devices. That is going to get you into timing, but you basically can put your device to sleep, use an external crystal to keep yourself periodically waking, or using a push button to push yourself awake and then do the transmission when you want at that point. The nuance of that complexity is going to be that your connection with the broker is going to be important to maintain. There is a point inside of the cloud connection where we actually are checking every 20 minutes, I believe it is.
Yes.
To confirm that we're still connected, and at the end of 20 minutes, we'll actually manually disconnect ourselves and reestablish a connection.
Gotcha.
So for that complex implementation with sleep, you would want to look inside of that cloud task callback, look at what is occurring there so that you can figure out how to reestablish the MQTT connection. Because you're basically going to want to go to sleep, wake up, reestablish the connection, do a broadcast, and then probably go back to sleep again. You're probably going to not want to be connected to the broker at all points because you're going to want to put the Wi-Fi device to sleep until you're ready to do a transmission.
Right.
And this 20-minute time period is, again, up to you. You can set up your cloud to whatever time period you want it to reconnect. So if you wanted to reconnect after a longer interval of time, then definitely you can do that to save more power. Yeah.
So hopefully by the end of the whole live stream, he'll have a better understanding of the architectural design and then some of the deeper detailed design inside of the basically like socket instances that they can figure this out. Otherwise, send us an email. We can do a deeper dive.
Yeah, for sure.
Okay, and that email address is livestream@microchip.com. Jared's a regular viewer, so he should be familiar with it. Should we take another question, guys?
Do we have any questions that relate to stuff that we've already talked about? Because we can take those, but if it's going to talk about the cloud or MQTT or things like that, we're going to cover that in coming forward, so we can probably answer those later on.
Okay, here's a simple question, and then we'll leave you alone. Will a Git Clone link be available for the PIC and AVR-IoT project?
Maybe not. We thought it was a simple question.
Yeah. So Microchip is trying to migrate a lot of our projects over onto a more public-facing Git repository. We have internal-based Git repositories, and this entire project is based upon that, so it would be pretty easy to migrate that history over onto it. Right now, it's the infrastructure, I suppose, for getting it out there. So
Sure.
as soon as possible. This is the best answer I can give.
Oh, okay, good.
Cool. Sounds good. So yeah, so we just talked about secure and kind of, and as Chris is talking about, we talked about smart a little bit earlier, and that's the embedded. That's going to be your AVR, your PIC. Then we just talked about secure, so that ECC 608 that's actually on those boards that allows that security component to it is really important, and that's what we just talked about. And if you want more information about security, we actually have Xavier, one of our security experts, did a great live stream a couple months back that we'll have a link to in the description as well. If you kind of want to just get a super big level primer on, or high level primer on security, really important stuff, especially moving forward. There's just constantly articles coming out now talking about how important security is when you're working with IoT devices. And it's actually not that scary at the high level, and if you understand it at the high level, a lot of the lower level stuff you don't really need to do because our engineers here have done a great job of writing that firmware for you. So just getting a high level understanding of it's going to be really important for any IoT project that you work on moving forward. And then next, I think we're going to talk about connected, so we can jump into that.
So once again, we just are going to continue through basically the application initialization process. So at this point, we're going to check the push buttons basically on startup. If you've pushed both of those buttons, we use the default credentials. So we basically just load MChip-IoT and Microchip as the default credentials. So that's basically for trade shows and things like that.
Okay.
Those are the common used SSID and authentication passwords.
Okay.
So this is basically like you getting into your router.
Right.
So this is your host name and your password. If you hold switch button 1, then that's going to put you into a soft AP mode. What soft AP does is it's a soft access point. So it actually allows the Wink 1510 on the physical board will host a website that you can connect to within that local radius. So you'll use typically your phone, and then you'll connect to the website that the Wink is hosting, and then that will allow you to load SSID and a password, and then you'll hit enter, and then that downloads the credentials to the Wink. So it's 100% isolated on that Wink device, and it basically will have the Wink device receive the credentials. It tells the microcontroller what those credentials are. The microcontroller updates the credentials in the back end, and then we will update to the cloud, and then your connection in the back end at that point.
Okay, cool. And just to like re-clarify that, so when I am using the AVR or the PIC-IoT board, my data that I see on the Google page, which we'll show in a little bit, that's not, Microchip doesn't own that, Google doesn't own that actual information. That's entirely generated from the Wink itself.
So the website, if you connect to it on a soft access point, will actually show an Atmel website.
Okay.
And that one is completely on the Wink.
Okay.
The one on the Google website is 100%, it is hosted on the website itself.
Okay, right,
but when you click the download, that is a configuration file that gets downloaded to you. So
Right, good
Microchip doesn't see
clarification.
any of that information. Google won't see any of that information. It basically just downloads the .cfg file to your system. So what that actually does is on the back end of the website, it'll parse through, grab the two text information, insert them into the text file, and then just generate and produce that file for you.
Okay.
And then you download it, and you can actually open that file, and what you'll see is one of the command line interfaces, the CLI that I discussed earlier.
Right.
Command that says Wi-Fi, and then the information you basically loaded.
Cool.
So that actually gets parsed over the UART terminal to the microcontroller. The microcontroller reads it and then loads those credentials.
Gotcha.
So once again, like you said, the CFG, all the credentials that you load into it, none of that goes anywhere onto the web.
Awesome.
That is all just downloaded off.
So when I give it a password and I give it confidential information, nobody's going to see it besides me.
No.
Is the important
Absolutely
part.
not.
Okay,
And if you
awesome.
just cut and paste the file or drag it in the curiosity folder, then it doesn't even have to stay on your computer.
Boom, there we go. Safe and secure. That's what we're all about. Cool, so we can jump back to the connected.
So basically you have your normal and then if you don't push any button, then basically the Wink device itself will store inside the module the last connection information. So
Okay.
basically when it powers down and powers back on, it just tries to reconnect to its previous successful connection attempt.
Cool.
So those are the 3 button actions, and then we'll get into the Wi-Fi initialization. So the Wi-Fi initialization, again, works a little bit with the callbacks. This works with the Wink driver itself, the software driver from the wireless product group. And then that one will have a Wi-Fi response callback. That is one function that basically correlates to if the access point has been disconnected or changed in any way.
Okay.
So that's a callback that the Wink driver itself does.
Okay.
So you just create that there. Then we are going to have our Wi-Fi handler task created. So this is actually a scheduled callback using the timeout scheduler I was talking about
cool.
earlier.
Okay.
Same principle in coding logic, but
Yeah.
now this is using the timeout scheduler
Okay.
Versus the way that the Wink driver system just works on that callback.
Okay.
So this one is the 50 millisecond callback. So this is just basically asking the Wink module from the microcontroller if it has any actions to perform. So if the Wink module has received any traffic over the internet, over your access point, then to indicate that it has data to exchange to the microcontroller, it will toggle an I/O pin. And
Okay.
this 50 milliseconds is us checking that pin and then handling the response from the Wink device.
Okay.
So we're just
cool.
servicing the call of the Wink.
Yeah.
And then, so that's it. So that's what gets us all connected at this point.
Cool. And so once again, bringing it back a level, we've talked about the PIC or the AVR, we've talked about the secure element, and now we're talking about that actual Wink module that's on both of those boards.
Right.
And this is the software that's Wink specific, so it's actually running on the Wink side of things.
Correct, yeah.
Awesome.
And so the microcontroller communicates to the Wink using the SPI interface. And so basically the Wink, anytime it has done the heavy lifting
Yeah.
of the internet-based communication,
Yeah.
it will just indicate to the microcontroller through an I/O pin,
Okay.
here's some data, I need you to do some work now. And then the
Cool.
microcontroller will then do data exchange using the SPI communication and then
Right.
go off the races accordingly.
Okay.
So then it will do the smart aspect of your data exchange.
Right. Awesome. Hey Wayne, we got another question in the booth.
Hey,
Perhaps.
we're back again.
You guys are just all over the place today, aren't you?
Well, and
We have technical questions.
Yeah, trying to keep you on your toes.
yeah, great questions, guys. Great. So let's see. What we
So we have a question from Fabian. Hopefully, I'm saying your name right in either those two versions. But is there a way to update the Wink 1510 firmware using the MCU, or should I just use the serial port?
So on the IoT board itself, you would have to update it using the serial port. If you flip the board back over, there's two header pins that connect to the UART lines on the Wink 1510. And so if you need to update the root certificates, you'll want to do it on that physical board through that connection. The reason for that is because I believe the baud rate it's in the 400,000.
Yes.
So it is outside the baud rate capability of the onboard
okay.
microcontroller.
Gotcha.
Otherwise, you could have an onboard microcontroller that also had UART lines that could flash that.
Right.
But the header pins are populated on the backside of the board. What we do is if we need to update root certificate on that board for development purposes, then we'll just basically put two header pins on it. And then you
Okay.
just connect it over the UART
Cool.
line like normal.
Awesome. Good question, Fabian.
Sweet. We have another one. We want to do another one, Ricky?
Sure. We'll throw another one at you. So in relation to security, is getting the UUID done only once at startup?
So the unique the UUID, we only do it once on startup because that's basically asking the EEC device what its name is. And then you basically are using the serial information from that device to append it on there. So we don't really need to ask it again to do that. The actual encryption aspect is going to be into the JWT token, which Medora will get into later. But we get into that when you're actually creating your connection with the broker. And that's going to be where we use the public and private keys and things like that for an encryption connected. The device UUID is just to ask basically, what is this IC specific serial number? And I'll use that serial number to make me as an IoT application product board unique.
Yes, absolutely.
Okay.
Sweet.
And as a hardware person, I didn't understand any of that.
Neither did
But
I.
I think it sounded great.
Yeah,
So-
trying to pretend.
So, yeah, no, I mean, I think just what Chris was saying, like that UUID is not generated. Like, I don't have to come up with that. That is the name of that secure device.
Right.
So all we have to do in terms of UUID is just ask it what its name is, and that's what's going to set it apart from everything else on the internet, right?
Yeah.
Basically.
Exactly. Yeah.
Cool.
Like you can continue to ask it what its name is, but it's never going to change.
Right.
It's the serial number on the IC device.
Okay.
And no two boards will have the same unique ID as the name suggests, obviously.
Right.
Great. Otherwise, it would be a semi-unique ID, I suppose.
Okay.
Great. Well, this last section is going to be super awesome, and Chris is going to wrap everything up for us, and then we can jump into some of those more detail-oriented stuff with Madura. So if you want to jump back to...
Oh, you went one ahead.
Oh, did I jump ahead?
There
Oh,
you go.
my bad.
That's okay. So this is basically where we're going to finish off. So this is just beneath where we were before. So this will say that if we are in that soft AP mode, that's what you see over on the left side. We basically will skip cloud initialization, we skip our main task, and we just go into normal run operation.
Okay.
And that's why if you look on the bottom, or the bottom of the screen, you'll see the call out runs. Timeouts, only the CLI task and the Wi-Fi handler would be called at that point. And that's because you're in soft AP mode, so the only thing you're actually doing is the Wink itself is hosting a website. It's asking you, the user, connect to it on the phone and give it credentials. When those credentials come in, it will then go through a reinitialization process where it will go through the cloud initialization and then come back into normal operation.
Okay.
So I just wanted to get that out there real quick. So in normal operation, though, we have cloud initialization, which will create a NTP timeout callback. It will create a cloud task timer callback, and then your main task callback.
Okay.
It will do those at different rates, and I'll explain why in just a second.
Yeah.
But that's all you really need to know. It basically just creates these 3 new time callback systems.
Okay.
So then we get into the LED task, which basically cycles the LEDs one more time, and it says, I'm done powering up, I'm done initializing myself, I didn't have any problems inside of my system, and my timeouts have all been created.
Yeah.
So then I get inside of my main while loop. Inside of that loop, you will only see one API call, and that is the scheduler getting called.
Okay.
So all it's doing is in the cooperative loop, it's running through the scheduler and says, when I hit the next timeout, I will handle that task. And then I will resume my countdown to the next task. So I'm just running through the list of scheduled tasks that you've created for me. So we've loaded each one of those as it got created in the initialization process.
Okay.
So now as a user, you don't have to worry about anything else except for those 5 abstracted APIs. And they're going to be called back at a specific rate. So I'll talk about what those 5 tasks are and why you really only have to focus on 2 of them.
Sure.
So the first one is your CLI task timer. So that is basically just parsing UART terminals over the USB line. So this is used to read the .cfg files that you drag and drop over onto the device, or to parse any of your over terminal commands that you write to it. That's it.
Cool.
The NTP time fetch is basically saying every half a second, I will ask the Wink to ask the global server, which is a network time protocol, what the current timestamp is. That is actually all of it does. It just says, Wink, go ask for an NTP time every half a second.
Cool.
The Wi-Fi handler is every 50 milliseconds, and that is a requirement to say, with the Wink driver, every 50 milliseconds, ask it if it has something it needs to do. So with the NTP time, the Wink sent out a request. When that request actually comes back as a response, I will know as a microcontroller through that Wi-Fi handler time. It will tell me, hey, there was a response to this request that you sent off. And then I will handle that response within my handler. So then it's abstracted there.
Cool.
So then you have your cloud task timer. So this is going to be where any of your complex communication with your broker, which is your internet provider. So in our case, with this example, it's Google. But that could be any one of your cloud providers that may have the root certificates loaded onto the Wink device, which is what we were referring to earlier with updating the Wink device through the UART terminal. And then you will have any of your unique broker information, which is MQTT, which Madura will get into.
Cool.
And then the final one is just your main task callback, and that just basically is how do I handle the LEDs and how do I check my push buttons. And then when do I take measurements from my sensors and request sending that to the server. So that's my main actual application behavior. So you as a developer would only really have to worry about that main application behavior. And then if you're changing the broker provider or the way that you're working on MQTT, then getting deeper inside of the cloud task handler. Otherwise, everything's abstracted to these 2 things, and they all will handle each other automatically for you.
Awesome. So if I am at home and I'm watching right now and I haven't played around with the board a whole lot, or maybe I've done the 30-second startup, but I haven't done much besides that, and I've decided that I'm going to still use Google, I'm going to keep the communication the same, the security the same, I'm going to keep everything the same, but now I want to take my board offline and I want to start taking data in from, let's say, like a soil reader or something. The only place that I'm really going to have to go into and get comfortable in is actually that main application loop.
That's true.
Exactly.
Okay, awesome, cool. So get comfortable with that, and we're going to talk about that a little bit more, but it looks like we have one question before we move on.
You know, it's funny that you talked about graduating your account because we actually have a question about that.
That's right.
So from Ariel, she's trying to graduate from the Google Sandbox, and she's able to get data to the cloud, but can't get the web page to work. So is there any chance that a simpler web page might be added to the Git repository or wherever we're holding the source code that's easier for beginners to sort of work with?
And by the way, Ariel, we apologize if you're not a she.
Yes, sorry, slip up.
It's just an American thing. All right, you got that, guys?
The website actually is configured to work with the Google Cloud Sandbox account, which is Microchip's account. You can create your own website essentially, and that's going to give you the capability of viewing your own graphs. All that is done, all that you need to do is basically you are sending the data in the form of JSON packets. So your website just needs to understand those JSON packets, which are going to be nothing but strings of key value pairs. And as long as you're able to parse those key value pairs, you should be able to display that data on your own website. Unfortunately, the website, which is currently on AVR-IoT.com page, is linked to the Microchip Sandbox account, so you won't be able to see the data on that particular website if you have already graduated. Because when you graduate, what essentially happens is your board is taken out of Microchip's Sandbox account, so it's no longer linked to Microchip's account, and at that point you're in your own account, so you're not linked in any way to the Sandbox account. So it's just a matter of what you want to do to design your own website. You can parse JSON strings, you can use JavaScript. If you want, if you're more comfortable with Python, then we have had people who have designed their own websites using Python. So as long as you're able to understand the data, you should be able to view it.
Okay, great. Any other questions before we move forward?
That is all we have.
All right, great. Awesome. So, yeah. So, do you want to hit that last slide, or do you want to jump straight over to Madura?
Go ahead and go to the last slide. Let's find out.
All right, cool.
Oh yeah. So this is basically, I was just trying to say that you know, those 5 API calls just basically make all the complexity of the AVR-IoT and the PIC-IoT project abstracted down in the simple 5 functions. So those again can just be your .cfg file, USB communications, parameter parsing is all handled by the CLI task handler. Your world timestamp is from the NTP callback. Your Wink driver action activities is just in that the Wink callback. TCP socket or cloud connection handler is all within the cloud task handler. And then data monitor exchange or behavior is all going to be abstract inside the main task.
Awesome. Sounds good. Great. Well then, on that note, Madura, why don't you take us a little bit more into specifically, so Chris just talked about the 2 most important tasks for most developers. Like number 1 is going to be that main application, and then the number 2 most important task is going to actually be that cloud handler, the cloud task. So Madura is going to, I think, jump in a little bit more detail about kind of what's actually going on the physical board as we see it and how that relates to that cloud task handler. So with that note, let's jump into the PIC AVR MCU IoT application.
Okay. So let's take a look at how all these callbacks actually appear on the hardware. The first step, of course, is going to be powering on your board. And when you do power on the board, I'm sure you guys must have seen this green LED show up as an indication that there is some power supply to the board. The next step, of course, is going to be initialization. And you will see a very distinct sequence of LEDs. The blue, green, yellow or amber and the red LEDs will be turned on and off in a very specific sequence, and this is going to happen twice. But this is just to show that the initialization is happening up. So basically all your peripherals are getting initialized, the microcontroller is getting initialized, Wing 1510 and ECC 608A chip is getting initialized, the onboard sensors are initialized. So once this sequence has been completed, you will see a red LED on the board, and notice that the label says error, but it's actually not error. All it is used to indicate is that you're not really connected to a Wi-Fi access point right now. So next step is going to be establishing a Wi-Fi connection to some network. And when you connect successfully to a Wi-Fi network, you will see that the red LED actually goes away and the blue LED, a solid blue LED turns on the board. which just is an indication to tell you that you are connected to a valid Wi-Fi network using the SSID and password which you provided. The next two steps are actually going to be opening a TCP socket and then establishing MQTT connection. So we are going to go a little bit into detail of what MQTT is in the next few slides, but basically you need a valid TCP connection, and then you need to establish an MQTT connection to talk to the Google Cloud. And once you have both of these, a green LED is going to turn on your board, indicating that you have a valid MQTT connection to the Google Cloud. So essentially at this point, you're ready to start transmitting or receiving data from the cloud. So next step is going to be exchanging data, and the way we do this from AVR or PIC-IoT boards is we use the two onboard sensors, which are going to be the light sensor and the temperature sensor. So both these sensors send the real-time readings of light and temperature, and this data is transmitted to the cloud in the form of JSON packets. So the data transmission rate is 1 second. So you will see the amber LED blinking at every 1 second just to indicate data transmission. It's just a visual indication. So we are not tied in any way to 1 second interval, so you can transmit the data at whatever time period you want. And this is where the callbacks come in handy, because this data transmission is going to be part of the main data task callback. So as long as you modify the rate at which that task is called, you should be able to modify the rate of data transmission to the Google Cloud.
Okay, cool.
So this is a little bit of code which you can take a look at. The first step is to open a connection, and we do this over port 443, which is the standard port provided by Google for establishing MQTT connection. And after that, you send a BSD socket function, and you open a socket at this point. So now you have a valid socket connection or a valid TCP connection, and the next step is going to be establishing an MQTT connection.
Awesome. Before we establish our MQTT connection, it looks like we've got another question in the booth.
Yes, we do. We're back again, and we have a question asking, can we create raw TCP/IP sockets?
Absolutely. You can totally create raw TCP/IP socket. So the first step is actually creating the TCP/IP socket, and then we open an MQTT connection. The way MQTT works is it uses TCP as the transport layer. So to open an MQTT connection, you absolutely need a TCP connection. So the slide which we were showing previously was all about opening just a TCP socket. And this socket is really necessary to open an MQTT connection. But if you just want to send data using TCP packets to some other server which understands TCP packets, then you can absolutely open just a simple TCP connection and then send your data by using TCP packets.
Great, that's an awesome question. Any others?
No, that's it for right now.
Great.
Thank you, guys.
So yeah, so now let's jump into a little bit more about the second step, which is going to be the MQTT connection.
Right. So we are talking to Google Cloud right now using the AVR and PIC-IoT boards. And Google Cloud supports two protocols. The first one is going to be MQTT. This is an acronym for message queuing, telemetry, and transport, as we all know. And the second one is HTTP, which is just a hypertext transfer protocol. We use this every day to interact with the web, to browse over the web. So we use MQTT for AVR and PIC-IoT communication with the Google Cloud. And the reason for that is MQTT is a lightweight protocol which is especially designed for resource-constrained systems.
Okay.
We use 8 and 16-bit microcontrollers, obviously, for this application. So MQTT is really suitable for us because it is lightweight, it works well with our memory-constrained systems, and it uses TCP as the transport layer, which is perfect because we have the Wing 1510, which has the whole TCP/IP stack in it.
Cool.
So once we have a valid TCP connection, now we are ready to start establishing an MQTT connection. So the connect MQTT function, which you see over here, is part of the cloud task callback, which is called every 15 milliseconds. And this function is actually going to send a connection request to the Google Cloud. If the cloud accepts our connection, then we are going to be able to transmit and receive the data. And this is done by MQTT reception handler and MQTT transmission handler APIs. So this these switch statements which you are seeing are just part of the cloud data task function, which runs at 50 milliseconds. And then sending and receiving of the packets, or rather sending of the packets, is done every 1 second.
Okay.
So notice that the cloud data task is actually running at a faster rate than your data exchange with the Google Cloud. So
Okay.
if anything goes wrong with the connection, if you lose MQTT connection or if you lose TCP connection, then you're going to get the cloud data task triggered every 50 milliseconds. And there you will come to know that your connection has been severed for some reason. And it will establish this connection before you send out your next published packet to the Google Cloud.
Okay.
So this application, because of the way the callbacks are structured, doesn't really follow a happy path, or it's not dependent on a happy path.
Yeah.
If you get stuck at some point, or if something goes wrong, the callback will get triggered and you will be directed to the appropriate callback once it's triggered to fix the problem.
Okay, cool. So it may not be a happy path in the sense that like we're all walking down the same line, but it sounds like there's almost a robustness built into the system where if something does go wrong, there's already things immediately built into there to solve that problem on its own, as opposed to everything crashing because one part of the system decides to stop working.
The happy
Absolutely.
path would be like the critical chain or something executing in a perfect sequential
Sure,
order. So
sure.
Traditionally we're used to sequential execution,
Right.
but with the callback system we are isolating each individual part.
Yeah,
So
yeah.
if something goes wrong in the cloud connection, then it will be managed and handled back within that cloud task handler.
Right.
So back in the main task, it actually is just checking to see if it's connected.
Cool.
So through the cloud task handler, it has told it, my connection is no longer valid, so you no longer need to worry about what you're doing
Right.
because you're no longer connected. Only worry about what you would do if you weren't connected.
Right. Okay, cool.
All right, so once you have a valid MQTT connection right now, you're basically ready to start exchanging data with the Google Cloud. So exchanging data is done in the form of publish and subscribe packets, and this is handled by the main data task callback. So every 1 second, you're going to be sending data to the Google Cloud, which is going to be nothing but just the light and temperature sensor data. So the visual indication is the yellow LED, which blinks every 1 second. And if you go to the AVR or PIC-IoT.com webpage at this point, you will see these nice graphs. These are nothing but the real-time light and temperature readings which are sent by the board to the Google Cloud. Again, if you want to change the callback, then all you need to do is change the rate at which the main data task is getting triggered.
Okay.
So we are sending data at 1 second, but you can send it at 2 seconds, 5 seconds, 1 minute,
Sure.
essentially whatever rate you want. And this robustness or this flexibility is actually provided by the callbacks, by the timeout driver which we are using.
Okay, cool. That just made me think of a question about what Jared spoke about earlier, but before I jump into like sleeping and things like that, if I decide to just send data at a less likely rate, will that save me power at all, or will it not make that much of a difference?
I mean, that would affect probably how you would do a transmission, but I don't think it would probably make that much of a difference. Most of your
Cool.
connection of the access point and the Wink itself being connected to the router,
Yeah.
and just having that constant data exchange is probably going to be where the majority of your power goes.
Sure,
So
sure.
you would want to go to sleep, wake up on a trigger event and things
Sure,
like that.
sure.
So for the sleep implementation, you can go to sleep, wake up every 1 minute or 5 minutes or whatever it would be. You then power on the Wink basically. The Wink,
Gotcha.
like I said before, if it had a previous successful connection, it will retain that. So just when you power on, you say Wink, come back on again.
Okay.
It will try to reestablish that connection. You can use the task, the cloud task handler to basically reestablish your connection once you become connected. Then you wake up, you do your transmission, you say, I've successfully done my transmission. Now I'm going to tell the system, go back to sleep. And then
Right.
it should take care of inside of its all callbacks, knowing that its connection was severed, so on and so
Sure,
forth. So
sure.
there's going to be a little bit of nuance of implementation,
Yeah.
but easily done.
Yeah, no, it sounds like because of the callback and the way that everything's set up, you can kind of jump into certain systems, and the rest of the system's smart enough to know what's happened and respond accordingly.
Yeah, so in
Yes.
Jared's example, they really shouldn't have to worry too much about having to go into the cloud task handler. They probably just have to work a little bit within the main task
Cool.
implementation and just getting the sleep aspects in.
Sure,
So I don't know too much about the PIC-24 sleep
Yeah.
on that one. I only know
Yeah.
the XLP part sleep.
No, that's cool. We got another question in the booth.
Hey, we've got another question from Isaac, and he I keep doing the gender thing.
That's
Sorry.
all right. I think that's pretty safe one.
Yeah, I'm assuming so, but you never know.
That's true.
If we want a secure connection with HTTPS, is SSL or TLS supported in this example, or do we need an external library?
So we actually do use TLS. If you're using HTTP bridge or if you're using MQTT bridge, both bridges actually have or require TLS. So this is a loose requirement from Google, but we have seen other clouds like AWS require TLS, like it's a hard requirement. So we actually use TLS for MQTT. You can absolutely use it for HTTP as well. The ECC 608 chip is actually capable of doing TLS security. So how the flow would work is on top of TCP, you will have TLS. And on top of TLS, you will have either HTTP or MQTT. And then you would be able to securely exchange your packets.
Great.
Can you take control for just a second
Yeah.
too and go back like 3 slides? I'll just point this out real quick.
Yeah.
To where the MQTT connection was being made. It'll say BSD connect. Hit back, back, forward, forward, forward,
whoa.
forward, forward. Sorry.
No, you're good. I
Right
went too
there.
far.
So right here is actually where it is. So I was just going to go back to the TCPIP and the UDP question as well. So this is actually being done if you look at the bottom of the screen where it says BSD_socket. This is actually where we are asking the Wink to create a socket and
Okay.
give us a socket response. So that PF_INET,
Yeah.
that is actually saying do a TCP connection.
Okay.
So there's actually another define inside that library system that will say do a UDP connection.
Yeah.
The Wink can
Yeah.
do it. You just have to ask it, I want a UDP socket or I want a TCP socket.
Cool.
So in this case, it was actually asking for the TCP, and then like Medora said, we stacked MQTT on top of that later.
Gotcha.
So furthermore, on the far right side of that is a 1.
Yeah.
That actually represents that we're doing a TLS secure connection.
Oh,
if we had passed a
okay.
0, then that
Cool.
would have actually said, I want to be an open connection.
Oh, awesome. Okay.
And
cool.
so that whether you want to be secure or an open connection is also managed slightly within the CLI for the authentication types.
Cool.
But just to answer that.
Yeah, that was a good wrap up.
And if we go back to the same slide,
It's a lot of
just
value.
yes, the line which says BSD H2NS 443, that's actually the secure port which is provided by the Google Cloud for establishing a secure TLS connection. So as long as we are using that port, we are doing TLS.
Okay, great. That was a great question and a good pick for a slide, I guess. That's
Yeah.
awesome. I know we are kind of getting close to the end of time, so if anybody has any other really pressing questions, let's definitely jump onto those, and then we can talk about the exciting, fun prizes.
Well, let's see. Ricky, do we have any additional? I mean, I think it looks like we have a few.
Yeah, we can do one more, I think.
Thanks for catching us off guard back here.
Yeah, I got you. That's what my job's for.
So Bruce wants to know, can he get some clarification on TLS? Is it available in MCC?
So
Aha.
TLS is actually, well, if you use the crypto authentication library, which is available in MCC, then TLS security is going to be available to you. You just need to go through the documentation of the ECC 608 chip on how to use that functionality. But the ECC 608 chip, which is the secure element basically on this board, is going to give you all the security functionality. And in Wink, if you use that specific function call and put that 1 as the function parameter, then you are going to get TLS.
So we create TLS through the Wink driver. So the Wink module itself has its own TCP library on it, and inside that library has some support for TLS functionality.
Okay.
And then we leverage the encryption device to get the tokens
Sure.
to create that secure
Exactly.
connection. there's not a software TLS generated solution.
Gotcha.
So,
Gotcha.
So just that deviation
Okay. Cool.
that I know of right now.
Yeah. And we can take a note offline to see if there's any good TLS videos that we've put out recently. I know security may have done some stuff with that. And if we can find anything, we'll throw that in the description as well to kind of answer that TLS question in more detail and have that available for people both now and if you're watching this and the live stream's already happened, check the description for that as well if you have questions on TLS.
Yeah, the wireless group may have an
Or
existing
wireless,
software solution.
Yeah.
It's just not one that I'm currently aware of.
Sure.
And we use the Wink and the encryption device.
Right. Awesome. So potentially both, but we'll have to look into that offline and post that to the video later on. Awesome. Well, this has been incredible. This is probably the second or third time I've had this conversation, and every single time I just am continuing to learn. So I think this is going to be one of those live streams that you probably want to watch a couple of times, especially if this is something that you're really interested in, something that you really want to become a master of the AVR and PIC-IoT environment. Definitely one you want to watch a couple times, take some notes, do some more homework, watch some of those other videos that we've talked about. And I think you'll be in a really good place to really become a master of that and be able to use it for all that it's worth. And I know our team has done some hard work in making sure that all the pieces are talking to each other well so that you don't have to do that work. And you can just touch the pieces of the system that you actually need to change for your end application. So thank you all so much for this great information. Do we have any winners? Or it sounds like we've had some questions, so hopefully we have some winners in the back.
We decided not to pick any winners today.
All
Yeah,
right,
not
well, I guess
today.
the live stream's over then.
I'm joking. So actually, we have quite a bit of interaction. So I'm gonna go with an even number of winners today. I said 5. We're gonna do 6.
Oh, there we go.
All right. So just before I name the winners, I want you guys to email us at livestream@microchip.com, and send us. This is important. Send us your entire address, a telephone number, where you can be reached. And we apologize in advance if for some reason we cannot ship legally to your location. We'll have to deal with that as it comes. But most of the time we're good. So send us an email. Let us know which board you want, whether it's going to be a PIC-IoT WG or an AVR-IoT WG.
Right.
All right. The winners are Chris Tucker. You want a drum roll, or you're just like? All right, sweet. Fabian Romo, Bruce Lavoie, and by the way, Matt, you can pick on me because I'm gonna mess up some names here. Ariel Raciopi, Jared Munch, Nuno Felicio, and Isaac Rose. So, Fabian, Bruce, Ariel, Jared, Nuno, and Isaac, please send me an email, and we'll basically get your prize out to you as soon as we can.
Yeah.
Right.
Let's see. Do we have anything else over here?
I don't think so. I think that's about it. That's all I've got, at least.
Awesome. This has been great.
Yeah, this has been fun.
Make sure you subscribe, like button. Please hit the like.
Yes, keep
Please.
us employed.
That's right. All right. I guess we'll throw it back to the stage, and we can close it out.
Great. Thanks, Wayne. Yeah, so if you guys subscribe or if you like the video, what that does is that helps us to continue to make great content. And for you guys, I know that Microchip as a whole puts out a lot of really good content, but sometimes because we put out so much good content, you can kind of get lost in the things. And if you subscribe, then we know that you're interested in the live streams, and we can continue to put them out and get them in front of the people. And I'll just make a quick plug for microchip.com/livestream. That's going to actually be our home base for all of our previous live streams. We have links to previous material that was important, previous board information and things like that. And we also have an email list that's on there that if you could jump on that email list, then you'll specifically be notified about when a live stream specifically is coming. So it won't just be a notification every single time a video is posted, but specifically for those live streams. And we've done stuff on medical, we've done stuff on power, or maybe we're going to do stuff on power. Can't remember on that. But we've done some analog stuff. We've done a lot of great 8-bit material. And I know we have some exciting stuff coming up in the future, so stay tuned for that. And we'll continue bringing you guys great content. Hopefully it's great. And if it's not, then let us know. And that's actually a great plug as well, is if you guys have things that you would love to see live streams on, please comment that below and give us some information, because we want to provide content and we want to provide value that you guys are actually interested in, y'all are actually interested in. So please comment below if there's a particular topic or subject or part number or whatever you might be interested in seeing a live stream on, and we'll definitely try to put the work in to make that happen. So with that note, I'm going to say goodbye, and we'll see you next time.